Okay, so this course is going to be about optimization on manifolds. And in particular, a lot of this is motivated by problems which are framed on matrix manifolds. So this is motivated by optimization problems on matrix manifolds. So as you probably know, the space of matrices, of all possible matrices, is a linear space. So the natural question to ask is why it is that one would like to consider optimization problems where you view it's like some appropriate space of matrices as a manifold as opposed to, say, a linear space or a vector space. So, of course, the space of matrices, right, is a vector space. So why consider optimization problems, sort of matrix optimization problems, on nonlinear manifolds? Okay. And a big part of this has to do with the kind of things which you're trying to optimize, the kind of scale-valued functions which you're trying to optimize, cost functions. So a big part of this is sort of the choice of cost functions, which often have symmetries or invariance properties that basically make the minimizers which you're trying to find, it's like non-isolated. Okay, and so let me just sort of say that numerically speaking, when you try to then construct an optimization algorithm and you happen to have minimizers which are not isolated, then this oftentimes affects the conditioning, it's like, or stability, it's like, of the numerical algorithm. Okay, so the other thing is that non-isolated minimizers, right, can pose problems in sort of stability and conditioning. For numerical optimization algorithms. Okay, and perhaps this is best illustrated with an example. Okay, so let's look at an example. So there's sort of perhaps a well-known method for finding the maximum eigenvalue of an operator A by maximizing what is known as the Rayleigh quotient. So you want to find the maximum eigenvalue, at least in norm, right, by maximizing Rayleigh quotient. Okay, which is a function on some vector, which is just the norm of A applied to the vector divided by the norm of the vector. Okay, and of course it's easy to convince yourself. It's like by sort of the sort of the linearity. It's like of the norm. It's like that that if v was a eigenvector, it's like you would get lambda v. It's like divided by lambda. It's like times the norm v divided by norm v, which is lambda, right? So so this attains its maximum. It's like at an eigenvector, and the value of that Rayleigh quotient, it's like at the maximum, is the maximum eigenvector. Sorry, eigenvalue. Okay, at least in norm, at least in absolute value. So the problem, of course, is that there's a scaling symmetry to this, right? So there's a scale invariance. So this plus function has a scale invariance. Right, so f of let's see, k times v is equal to f of v, right, as long as k is not equal to 0. Right, so what basically happens is that if you have a vector v, it's like then the entire linear subspace associated with that, with the exception of the 0, right, is going to have the same Rayleigh quotient. Okay, and again, that's to be expected because the eigenvector associated, it's like with a particular eigenvalue, is not unique, right? So if v is an eigenvector, it's like then k times v, as long as k is not 0, right, it's again an eigenvector associated with the same eigenvalue. So that's not so surprising. Okay, so in any case, it's like that basically means that there's a direction. It's like along which the Rayleigh quotient of the cost function doesn't change, and that poses a problem. For example, it's like if you were using the Newton method, because you have to invert, essentially the the Hessian. It's like of this cost function. It's like and that Hessian will have it's like a component. It's like there'll be an eigenvalue. It's like which is 0. Which is corresponding to this direction. It's like where the Rayleigh quotient doesn't change in value. Okay, so so that causes a problem. It's like in the conditioning. It's like the problem of the numerical method. It's like when trying to solve this. So how can you deal with that? Okay, so there are sort of two approaches for dealing with this, which are in some sense prototypical of the kind of problems which we're going to look at in this class. Okay, so there are sort of two ways of dealing with this scale invariance. So one very common way is to constrain the optimization problem, right? So you want to look for the minimizer of this Rayleigh quotient, but not over all matrices, but over matrices. I'm sorry, not over all vectors, but vectors maybe with unit norm. Okay, so that's very common, right? So you constrain the problem to sort of optimize over vectors with unit norm. Okay, so this converts the problem. It's like for this problem, it's like from optimizing over all vectors, well, all vectors but a 0 vector. Okay, so to vectors which are in the unit norm, which have unit norm, which is the sphere. Okay, so this involves an optimization the sphere. And the sphere, of course, is now a nonlinear space, right? Nonlinear manifold, but this sphere obviously is also embedded into the space of all vectors, right? But this is an embedded manifold. Okay, so so again, one of the approaches it's like we're going to take is to deal with these things which are known as embedded manifolds, and we're going to try to formulate algorithms which deal with this idea of embedded manifolds. Okay, so the other approach is to quotient out this scaling symmetry, right? Okay, to sort of form a problem on a quotient manifold. Right. Yeah. So those are really sort of the two main approaches. And I should say that yeah. So we're going to formulate optimization problems with symmetries by viewing them as living on some sort of either embedded manifold or quotient manifold. So those are also going to be the two major classes of manifolds we're going to work with, and all of them are at least for the purposes of this class, are going to be matrix manifolds in essence. Okay. So let me maybe say a little bit more about this idea of quotient manifolds. And the basic idea behind this is that if you have a symmetry, so given a symmetry action, right? So as an example, again, the scaling symmetry, if you take something and you scale it, right, for all different scaling parameters, you get what is known as the group orbit, right? We obtain a group orbit. Okay, and this group orbit forms what is known as an equivalence class. And the basic idea then is that you want to, instead of looking at the fundamental objects as the vectors themselves, look at the objects on which the cost function is defined as being defined on these equivalence classes. All right, and then we formulate the optimization problem. On the equivalence classes, on the set of equivalence classes. Okay, and this gives you a problem on a quotient manifold. Okay. So I will also say that before I go on, it's that when you think about this thing on the sphere, what you're really doing is that there's again this idea of this equivalence class, which are all vectors which are related to each other by some sort of non-zero scaling factor, right? So what the act of optimizing on the sphere does for you is that for each of these equivalence classes, it is going to choose a representative element of it, which is to say that instead of thinking of working with this set of things which are of vectors which are related by the scaling symmetry, you just pick one element in that set and you work with that one element. Okay, so you can think then of the unit vectors as being a representative element of an equivalence class, right? So you can think of the unit vectors as being a representative element of an equivalence class. And I should say that there is sort of a slight caveat, right? Because really, even when you work with the sphere, there is still a symmetry to the problem, okay? But it's now a discrete symmetry. So what I mean by that? So if you have a unit vector, right, and you also know that the negative of that unit vector is, so if a unit vector is a eigenvector, it's like of the matrix, then the negative of that is also an eigenvector of the matrix. All right, so there's still a redundancy when you do optimization over the sphere, because v can map to minus v and it will still give you the same Rayleigh quotient. Okay, so so you have a situation now where there's a discrete symmetry, and the reason why that's okay, why it's okay to work with optimization on the sphere, when we said that there was this issue of degeneracy and non-isolated, is that if you have a vector v, then minus v is isolated away from v as long as v is not 0. Okay, and again, it's like the optimization problem which you have is already, it's like removing the point v is equal to 0 from consideration, because of course it's like the Rayleigh quotient is not well defined there. Okay, so it's actually okay that you have this redundant representation of the eigenvector, right, either v or minus v, because while there are sort of 2 points which now still have the same value in terms of Rayleigh quotient, these 2 points are not, they're disjoint from each other. Okay, so the right thing, it's like the right space in some sense to be working with, is what is known as the projective space. Okay, where you quotient by, again, this full scaling symmetry. Okay, and so it's maybe not 100% true that these unit vectors are really a representative element. They sort of are a representative element up to this sort of ambiguity in terms of the plus and minus signs. Okay, but nevertheless, it's like they're sort of isolated, so things are still reasonably good. Okay, so anyway, so those are sort of the two main classes of manifolds we're going to work with. We're going to work with embedded manifolds, right? Which is the easiest example of embedded manifolds are that these are the level sets of some sort of function, and and the other example are these quotient manifolds, where you're dealing with these things more abstractly. Okay, so with that in mind, it's like, let me then say a little bit about what are some of the challenges, or so what are some of the tools, it's like, which come into play when you then try to do optimization on manifolds as opposed to vector spaces. Okay. Okay. So so perhaps it's like the way to sort of think about this are to just look at some of the simplest examples of optimization algorithms on vector spaces, right? So let's look at, say, the gradient method. sort of gradient descent, and the Newton method, right? So these are two methods which are perhaps familiar to you. And then let me just sort of say, well, what happens or what you need to do, it's like to think about generalizing this to a manifold. Okay, so so the gradient descent method, obviously, as you might imply, as the name implies, right, requires you to define the gradient, right? So we need to define the gradient, and then in Newton's method, we need to sort of define the Hessian of a scalar value function. Okay, so and you might ask again, you know, what makes this challenging? Okay, so if you think about what the gradient of a function is, right? Right, we we oftentimes think of it as as defining a directional derivative, okay, and let's just say in some direction r. All right. So what we want, if you will, is that we want that this is f of x plus some epsilon r minus f of x divided by the epsilon times the norm of r. And we want to take the limit as epsilon goes to 0. Okay. So so we want to define something which looks like this. Okay, and the basic idea, or the real challenge, is that you have to, okay, so f is assumed to be a scalar value function, so taking the difference of two scalar value functions at different points is still okay. Okay, so the real challenge is that you have this length, if you will, which you have to measure, right? So in defining the gradient, right, we need the notion of an inner product. So you have an inner product here because this is a vector. Inner product of inner vector gives you a scalar, right? And a norm. Okay, the norm is not such a problem. If you already have the inner product, it's you can induce the norm from that, right? So you can define the norm of R as the inner product of R with itself, right? So so that's a fairly common construction. So basically, it's like you need an inner product to make sense of this left-hand side. And then if you have that inner product, it's like you can also make sense of this right-hand side, in particular this norm term here. All right, so this leads to the sort of smooth specification of an inner product on a manifold. Sort of leads to the notion of a Riemannian metric. Okay, so that's one of the things that's like which we're going to have to deal with. And then, all right, so so the point is that if in any case, the point is that if you have a Riemannian metric, then you can define this gradient and we can start talking about gradient descent. Okay, and then the other thing it's like we need to deal with is to define the Hessian. Okay, so the Hessian is a little bit harder. Okay, so the Hessian involves taking the difference of sort of vector valued vector valued function at two different points. On the manifold. Okay, and the point is that you can't really do that, because if you have some curved space and you have 2 points, then the vector valued thing is like lives in what is known as the tangent space to that manifold, and those two tangent spaces in general, because the space is curved, do not agree with each other, right? So if you have a vector in one tangent space and a vector in the other tangent space, there's no canonical way of saying that I'm going to take the difference of these two vectors. Okay, so there's no canonical way to take such a difference. Okay, and so in order to make sense of that, we need to introduce an affine connection. So we need to introduce an affine connection in order to make sense of this. Okay, and if you happen to be in the situation where you have a Riemannian metric to begin with, this is in the framework what is known as Riemannian geometry. Then there is a natural affine connection associated with the Riemannian metric, which is what is known as the Levi-Civita connection. So given a Riemannian metric, right, there is the Levi-Civita connection. Okay, all right. Okay, so the other thing it's like which happens is that in order to make these calculations more efficient, even though it's like you can frame the problem formally, it's like in terms of Riemannian metrics and affine connections, and as a particular case, the Levi-Civita connection, there are sort of two basic operations one needs to be able to do, okay, which are associated with these two objects. Okay, so the first of which is that the Riemannian metric, amongst other things, leads to the idea of geodesic transport or geodesic flow. So the Riemannian metric, of course, is a way of gives you a way to measure lengths, right? So if you can do that, you can start thinking about, well, what does it mean to have the shortest path between 2 points, okay? And that gives you one notion of what is known as a geodesic, okay? So it gives you a way of measuring lengths. Right, so this leads to the notion of a geodesic, which is like a length minimizing curve. Okay, so in any case, what that does is that you can talk about, say, given some initial point and some vector, you can ask it's like whether there's a geodesic which goes through that point. It's like with a tangent to the geodesic curve, which is that tangent vector. Okay, so and when you do that, you now have a parametrized curve. It's like which is a geodesic curve, and you can define what is known as the Riemannian exponential. Okay, so this leads to, it also leads to the idea of a Riemannian exponential. Okay, and what the significance of the Riemannian exponential is that it gives you a way to think of the tangent space at the point M to the manifold M as being locally identified with M cross the point M cross the big manifold M. Okay, and sort of and you can sort of think of it as mapping this point, it's like, and this vector to a point on this curve gamma at time 1. So if the curve gamma at time 0 is m, right, then we say that the Riemannian exponential of this vector times based at m is gamma at 1. Okay, so there's a way to basically locally identify the tangent space now with some neighborhood, it's like of the point m. That's the point. So there's a local diffeomorphism between the tangent space TMM, right, with a neighborhood, I should say between the neighborhood of the origin of the tangent space with a neighborhood of M. Okay, all right. So so that's one of the things you can do. It's like with a Riemannian metric is you can look at what is known as the Riemannian exponential, and then locally that gives you a way to identify the tangent space, right, of a manifold with some set of nearby points. It's like around the manifold. Okay, and of course it's like it's not always easy to solve. It's like, or to compute this Riemannian exponential, because in principle what you have to do is that you have to solve the initial value problem associated with what is known as the geodesic equations, okay, which is a set of differential equations on the problem. And so that might be a hard thing to compute. So numerically speaking, instead of using this Riemannian exponential, what we're going to oftentimes try to do is to construct something which is approximating this Riemannian exponential. You know, it's like, or constructing or approximating this, you know, it's like local diffeomorphism between a neighborhood of the origin of the tangent space with this neighborhood of M, and that's going to be this idea of a retraction. Okay, so we'll approximate this local diffeomorphism using what is called a retraction. Okay, and then the other thing it's like is this idea of parallel transport. And parallel transport is going to be related to the affine connections which we considered, right? So we also considered, so parallel transport is going to be constructed from our choice of affine connection. So, so the way to sort of think about this is that it's the idea of parallel transport is related to this idea of what it means for a vector to not change in direction. Okay, and the affine connection more or less gives you a way of, you know, as I said, it gives you a way of relating tangent spaces at two different points. Okay, so if you parallel transport a vector along a curve, right, then what you really want to do is to have that the, in some sense, it's like the derivative, it's like of that vector field to be 0. Okay, so if you say that the derivative of a vector field is 0, right, then we're saying that the vector field is not changing in direction. So in any case, it's like this notion of affine connection. It's, I guess, a way of defining what it means to, it's like to talk about derivatives of vector fields in some sense, okay, and this idea of parallel transport has to do with the idea that this derivative of the vector field vanishes, okay, and the net effect of this is that it gives you a way of saying, given an initial vector, it's like I can transport it in some natural way along a curve in such a way that I'm not changing the direction of the curve. Okay, so that's what's meant by parallel transport. And again, it's like this is something which, in principle, if you want to do it correctly, requires you to solve some sort of differential equation. So in practice, what you can do instead is you can again try to approximate this thing by introducing a vector transport instead. Okay, so in practice, right, one tries to approximate using sort of vector transport. Okay, so the strategy, if you will, is that you first frame the optimization algorithms in terms of these exact objects, like the Riemannian exponential and parallel transport. You prove certain nice properties about it, and then you then take the algorithm and you replace, the local diffeomorphism. It's like which comes from the Riemannian exponential with a retraction. You replace maybe the parallel transport with this vector transport, which is easier to compute, and then you ask again whether or not this more practically implementable algorithm has the same type of convergence properties. Okay, and oftentimes you can show that under sort of mild assumptions about the retraction or the vector transport operator, you will still have the same rates of convergence. Okay, so that gives you sort of a high-level picture of why it is that we're interested in looking at optimization algorithms on matrix manifolds. And again, it's like this oftentimes shows up because the cost function has some sort of symmetry and invariance. And if you were to directly try to solve this problem with a cost function with that invariance, you have non-isolated minima, which can pose stability problems with your numerical optimization algorithms. So what you want to do instead is that either you want to try to find some sort of embedding manifold formulation where there's only essentially you essentially only have isolated, it's like minimizers, right? Or it's like you formulate this in terms of quotient manifolds, where you look at the quotient space which identifies it's like all points which are related by this kind of symmetry. And in either case, it's like you have a problem now which is formulated on typically a nonlinear manifold. And so we want to extend some of the standard algorithms which we're familiar with for optimization on linear spaces, like say gradient methods and Newton methods. And as I've sort of alluded to, that involves introducing certain differential geometric tools, in particular this idea of a Riemannian metric and an affine connection. And then finally, it's like in order to make these things practical, we're going to consider approximations which are based on easier to compute things like the retraction and the vector transport. So let me just stop here and we'll continue later.